Hey folks, it's another fun video on intermolecular forces, IMFs. Yay! Let's get started. In this one, we're going to be looking at a special kind of dipole-dipole force. We're going to be looking at hydrogen bonding. So hydrogen bonding is very cool. Hydrogen bonding is stronger than a regular dipole-dipole interaction, and therefore stronger than a London dispersion force interaction. It is, in fact, as I said, a special type of dipole. And so we only see hydrogen bonding when we have hydrogen bound to three different elements. If we have hydrogen bound to our good friends nitrogen, oxygen, or almost messed up, or fluorine, these will make hydrogen bonds here. And so the result of this is these are very electronegative elements. These are the three most electronegative elements. So these are going to be very polar bonds. The result is that we get a very large partial positive charge on this hydrogen. A lot of electrons get stripped away. And we get a very large partial negative on these very electronegative elements. If just by the size of the delta you were going to compare this to some other elements, let's say we compared this to a phosphorus hydrogen bond. In this case, our dipole and our partial charges are much smaller. They're going to be much smaller, and they're not going to have the same strength of interaction. So water is one of our best friends who exhibits hydrogen bonding. We have OH bonds. This is a very, very polar bond. Another common friend who does this is our friend ammonia. These are two of the molecules that we've looked at. But we also see hydrogen bonding in much larger molecules that have much greater significance. But before we talk about those, one thing that's important to note is that in hydrogen bonding, we need to have lone pairs on one of these electronegative elements, and in order for them to really do this hydrogen bonding. So this oxygen has lone pairs, and that enables it to interact. It has a lone pairs and partial negative, while this hydrogen has partial positive. Without those lone pairs, it really can't form the same strength of hydrogen bonding interactions there. So it's really important that there be lone pairs on either our oxygen, our nitrogen, or our fluorine. But let's look at those bigger molecules. So here we've got two, oh my gosh, if my fingers work, we'll look at them. Here we've got some examples of some larger molecules. We've got ethanol shown up here, and we've got some DNA base pairs down here. Specifically, if the camera's a friend, we've got guanine and cytosine. So take a look at these and see if you can identify where hydrogen bonding interactions will take place. And pause the video and think about that now. Great. So you've thought about it. Let's look at our ethanol first. In ethanol, we've got OH bonds. So these will be polar, and we have lone pairs. Great. We can have the potential for hydrogen bonding. So we're going to have a partial positive on our hydrogen, partial negative on our oxygens. And so we'll see an interaction with hydrogen on one molecule being attracted to oxygen on the other, and the reverse up here. This hydrogen wants that oxygen, this hydrogen wants that oxygen. So these form very strong, very stable relationships between them. Well, let's look now at our DNA. Holy cow, there's a lot going on here. So if you didn't see everything, that's legit. But we've got NH bonds here, we've got NH bonds here, and we've got NH bonds here. Those are three places where we may have very positively charged hydrogens. Let's put some labels on those. And then, where might we have very strong negative charges? Well, there's a nitrogen with lone pairs out, so you could potentially participate in hydrogen bonding. This oxygen is sitting pretty with just lone pairs, so it could potentially play. And the same goes for this oxygen down here sitting with just lone pairs. And that, if you look, these are right across the way from each other. We've got a negative directly across from this positive, a positive directly across from this negative, and a positive directly across from this negative. This is how DNA strands are actually held together, through a whole bunch of hydrogen bonding. Without these hydrogen bonding interactions, which are incredibly strong, DNA would not be stuck together, it would fall apart, life wouldn't exist, everything would kind of suck. Or maybe it wouldn't, because we wouldn't be alive. But without hydrogen bonding, there is no life. So that is really important for life and also just understanding hydrogen bonding. So great, hydrogen bonding is a special type of dipole-dipole interaction. It is stronger than a regular dipole, stronger than London dispersion forces. And again, it is a special dipole, and it is part of our family of intermolecular forces. Yay! I hope you enjoyed this video. I hope you understand how DNA is held together now by special dipoles. And I hope you're feeling just really great about everything, and everything's super wonderful in your life. Have a great day. Bye.